In Calculus 1 and Calculus 2, we look at single variable functions that help us to describe curves in two-dimensional space. Earlier in Calculus 3, we saw vector-valued functions, which help us to describe curves in three-dimensional space. Now we're going to take a look at functions that require more than one variable and see that they help us to describe surfaces in three-dimensional space. Multivariable functions give us a way to expand on some ideas we're familiar with from single variable functions. For instance, we all know the familiar relationship distance equals rate times time, which we can think of as a function of the variable t, where r is the fixed rate at which we're traveling. Of course, it's very rare that when we're taking a trip, we actually drive at the same speed the entire time. So multivariable functions allow us to think about distance as a function of both r and t, so that we can contemplate what happens as both our time varies and our rate varies. Similarly, you might have seen in an algebra class a cost function where cost is equal to some fixed cost L plus some price P times X, where X represents the number of goods produced. However, the price P may vary due to a number of factors like the cost of ingredients or the cost of goods to produce whatever you're making. So we can then think of cost as a function of both P and X. We could take this one step further where the fixed price might vary as well, so that cost then becomes the function of three variables, L, P, and X. So multivariable functions have a lot of real-world applications. Over the next several videos, we'll take a dive into the mathematics of these functions so that we can understand their structure and the implications that those have for real-world applications. We'll spend most of our time looking at functions of two variables, which come in the explicit form z equals some function of x and y, or the implicit form f of x, y, z is equal to 0. Those forms can be extended to as many variables as we choose, where a function of n variables can be written in its explicit form as z equals some function of x1 through xn, or in the implicit form f of x1 through xn is equal to 0. Just like functions of one variable, we have to concern ourselves with the idea of the domain of a function that has more than one variable. For a function of two variables, we're going to define the domain to be the set of all points xy belonging to r squared, the familiar Cartesian plane, where f of xy is a real number. While much harder to visualize, the domain then of a function of n variables is going to be the set of all points in Rn that produce a real number when plugged into the function. While the domain of a function of two variables lives in two-dimensional space, the range itself lives in one-dimensional space. The range is going to consist of all real numbers that correspond to some point in the domain. Similarly, while the domain of a function of n variables lives in n-dimensional space, its range is also still within one-dimensional space and consists of every real number that is the output of some point in the domain. Because they're the easiest for us to visualize, we will focus on the domain of functions of two variables, and so we'll think of those as all inputs in the xy plane that you are allowed to plug into the function. When identifying the domains for these, we'll look for the same type of things we did when we examined the domains of functions of one variable. In particular, we'll be looking for division by 0, even roots of negative numbers, and logarithms of negative numbers to help us figure out what isn't in our domain. Let's take a look at an example. Here we're going to try to find the domain of the function f of xy is equal to 3x squared plus y squared plus 5. We want to find its domain, its range, and we're going to figure out what geometric surface this represents. So notice that because this function consists of powers of integer powers, in particular, integer powers of x and y, and all we're doing is taking sums of those, this is a polynomial. It's a two-variable polynomial. And just like for one-variable functions, polynomials are defined for all values of x and y. So our domain is going to be all of R2. Any point x and y will make a valid input to this and produce a real number. For the range, we want to notice that x squared plus, or 3x squared plus y squared is always a positive number. Regardless of what values of x and y I plug in there, that's always going to produce a positive number, or a number that's greater than or equal to 0. That means that the outputs of this function are all greater than or equal to 5, because we're adding a positive number, or 0, to 5. That means that our range is going to be the numbers from 5 to infinity. To describe this, we have to remember that when we graph a one-dimensional or a one-variable function, when we graph that, that produces a two-dimensional curve where each point represents an input and an output. When we graph a multivariable function, the same thing is going to happen. So a two-variable function is going to produce a three-dimensional surface where each point on the surface represents some combination of an input, which is of the form xy, and an output, which is of the form z. So looking at this should be a surface that we recognize. We can think of this as 3x squared plus y squared plus 5 is equal to z. So we know that because that's linear in z, this is going to be a paraboloid. Which I'm spelling wrong. And because the terms are added, we know that it is elliptic in form. We know that rational functions have restricted domains when they're single variable functions. Let's see what happens when we have a two-variable rational function. So because we're trying to produce a real number, we know that our denominator, x squared plus y squared minus 4, can't be 0. So let's look at what happens when it does equal 0. That will tell us what we need to rule out from our domain. So when it is equal to 0, we get that x squared plus y squared is equal to 4. And we know that this is a circle with center 0, 0, and radius 2. So our domain is going to be everything except that circle. So our domain is going to be all of the points in R2, except for the circle x squared plus y squared equals 4. Let's look at an example of a radical function. We know for single variable functions that for a value to be in the domain of a radical function, what's under the square root has to be positive, and that's going to be the same for a function of two variables. So in other words, we need 9 minus x squared minus y squared to be a positive number to be in the domain. We can rearrange that. Negative x squared minus y squared is greater than or equal to negative 9. Dividing through by negative 1, we get that x squared plus y squared must be less than or equal to 9, and that's the domain. So our domain is a disk with center 0, 0 and radius 3. We get the whole disk, not just the circle here, because of the inequality. The inequality means we get everything inside of the circle and we get the circle itself. So we get the disk with center 0, 0 and radius 3. For our range, what we have to recognize is that the function actually represents the surface here is the top half of the sphere with radius 3. Which means that along the z-axis, our values are going to go from 0 to 3. So that is the range of this particular function. All right, summarizing what we know. Functions of two variables are functions from r squared, the set of all points x, y, into r, just a set of real numbers. So their input is a point and their output is a number z, which is going to be the function value. And when we graph them in 3D, we're graphing the surface z is equal to f of x, y. We can expand those ideas into functions of n variables, where f is a function from r to the n into r again. So our input is now a multivariable n-dimensional point, and our output, however, is still a single number z, which is equal to the function value. Here, however, we can't graph them because graphing in more than 3 dimensions is extremely difficult, impossible, maybe. Coming up in the next few videos, we're going to look at a technique for helping us understand these 3-dimensional surface graphs, as well as start to look at calculus on multivariable functions, including limits, continuity, and derivatives.